Welcome, folks. This is Mr. Bergman, and we are here in Woodland Park High School at what time is it, Mr. Sams?
I was going to ask you the same thing.
It's like 6:30 in the morning. Isn't it the greatest time of the day?
Mm-mm.
What do you mean, no?
Because I've got about this much of my coffee finished, and I got about that much to go.
You are such a wimp, I tell you.
I was here till 10:30 last night.
Well, that's because you're such.
Home?
Yeah. Well, I was in bed at 9 o'clock. Are you kidding?
Yeah. See,
I'm a morning person. You see, Mr. Sams is not a morning person. As you can tell, he needs his coffee. And we're trying to finish up our last podcast today of this whole unit. And we're like under the gun because, you guys need to hear this soon. So we are in trouble. So we figured we'd just get here at 6:30 in the morning. And so I proposed it, and he said yes, which was, I said yes, and he said, well, what did you say? Yeah, the thing. So, as you can tell, Mr. Sams needs some help. We knew that last time, actually. It's a different kind of help he needs today, though. He needs caffeine, which is actually a molecular compound, is it not?
It is.
And so, when you're studying molecular compounds, we're going to be talking about the forces that hold compounds together, molecular compounds and such. So, that's kind of cool, isn't it? We're going to be talking about things like caffeine today. Huh, interesting. All right. Well, with that said, let's focus in on today's lesson. Today, folks, we're going to talk about intermolecular forces. Can you say intermolecular forces, Mr. Sams?
Intermolecular forces.
Okay, well, you sound so chipper today. It's amazing.
I'll work my way through this cup.
Hey, what the heck is intra? There's actually intra and inter.
Yeah, it's kind of like an interstate highway. If you drive on an interstate highway, like if I go up to Denver and I hop on I-70 and I go east.
Yeah, interstate.
Interstate, eventually I'm going to end up in Kansas.
But this is intra.
Right.
Yeah, okay.
Right. And then eventually I'm going to end up in another state. So interstate highway, you go from one state to another state.
Yeah, I see.
Okay? But an intrastate highway, like Highway 24 that goes to Woodland Park here, is no, that's not a good example. Highway 67 that goes out of Woodland Park here is a state highway. If you leave Colorado, you will no longer be on Highway 67.
That makes sense.
You'll be in like a Wyoming state highway or something.
Yeah. Another example that would be interesting. Do you know that Mr. Bergman played basketball in college?
Did you really?
Yeah, I did. I played basketball. I went to Oregon State University and I played basketball. Mm-hmm. But
like intramural basketball?
You see, there are two kinds of basketball that takes place at Oregon State University. There's what they call the intramural team, and then there's the intercollegiate athletic team. The intercollegiate, who do you think they played?
Intercollegiate's probably playing other colleges.
Yes, so Oregon State played UCLA.
All right.
And then there was intramural, and I played on intramural. Probably, because I suck at basketball, and I'm 5'7".
And how tall are you, Mr. Bergman?
5'7"
okay. That's what I
and
thought.
a half.
Yeah.
I think I've lost the half since I'm
See,
now
I'm
old.
6'3", and people always think I'm good at basketball. I'm really bad. So, someone accused me of being a basketball player the other day, so I had to get these geeky glasses to set things straight. That no, not a basketball player.
Well, you see, I'm a pretty good outside shot. Or at least in my day, I could shoot from the outside. However, I'm 5'7".
I had to get these so there would be no mistake.
Okay, but let's talk about what we're talking about in terms of molecules.
Okay.
When we're talking about molecules, we're talking about a covalent compound, okay, or a covalent bond.
Okay.
So this is two water molecules,
yeah.
And the bond that we're talking about is this bond that holds the H's to the O's.
Okay, so
the
that's
O is
intramolecular because it's within that same molecule.
Right, because when I played intramural, I played other. I was on the McNary Hall team.
Right, all within your school.
And we played the Samson Hall team or whatever, you know.
Right.
Or whatever the heck the other teams were, I can't remember. And then intermolecular.
You know what I played?
What?
Intramural Ultimate Frisbee.
No, that would be cool.
No, that's a good game. I can actually play that
I
game.
do like.
Because I don't have to. There's no ball involved.
Yeah, I do like that game. I played that. Now, what we're talking about today is not the covalent bond, but the bond that holds one water molecule to another water molecule. Hence, the intermolecular bond. So, folks, you can see us now holding up two molecules that have the bent 105 shape. Now, the bond in between here that I'm pointing to with my pen that holds this ball to this ball is the covalent bond, the intramolecular bond. The bond we're talking about now is the bond that holds these two molecules together. It's as if there's a dashed line, or maybe a tiny little thread or string that is holding this molecule to this molecule. That is called the intermolecular bond. That's what we're talking about today. Okay? Okay, so we're back on the screen. All right, now the key thing to understand this entire thing is a chart. Now, this chart was developed by me. It's the Beckmanian scale of bond strength, I like to call it. And basically, we want to look at bonding, and there are several varieties of bonding, and you know most of this, and we've talked about this at some length for quite some time. There are covalent compounds, or bonds, and in a covalent bond, what's the story on that? That's going to be what type of substances?
Two nonmetals.
So that'd be nonmetal to nonmetal. And I want you to write strength of, actually, we'll wait there. And then our ionic will be
metal, nonmetal.
Metal to nonmetal. Metallic will be
just metals.
Metals, and we've kind of seen this before. Now, I want us to add some numbers here. Actually, let's bring another box here. And we're going to call these network solids. And I want you to write the number 100. Okay? So if we were to measure bond strength on a scale of 1 to 100, or 0 to 100, a network solid, which is made of nothing but covalent bonds, would have a strength of 100. It would be the strongest of all bonds.
Right.
Okay.
I know this is just kind of an arbitrary number that you made up for reference points, isn't that?
Yeah.
Is that correct?
Yeah,
okay.
There is some validity to the numbers,
right.
but it's roughly because they change. Not all network solids are the same strength.
But it's very helpful to compare one type of bond to another.
Yeah. The second highest would be an ionic bond, and we're going to put the number 85 here. So ionic bonds are very strong, however, not as strong as a network or a covalent bond. These is all covalent bonds. And then the metallic would be a little bit weaker, and that's a 65.
Okay.
Okay, but now we have an issue, is that covalent kind of breaks apart.
Yeah.
And it breaks apart into both polar and nonpolar. And now what we're actually talking about is the intermolecular forces. So below this line, not including these, the network solids over here, these are intermolecular forces.
Right. The other ones are intra.
So these are the intermolecular forces. Right. We have polar molecules and nonpolar molecules, and we've learned them. Let's talk about the nonpolar ones. That's held together by something called a London dispersion force. More on that later. But they are the weakest of all forces. Their strength is 0.1. Very, very weak compared to 100, isn't it? And then when you have polar molecules, there are two varieties. There's hydrogen bonding, and there are dipole forces. And for hydrogen bonding, that's a strength of 5, which actually for intermolecular forces is very, very high. And but it's still a 5 out of a scale of 0 to 100. And a dipole force is a 1.
Okay.
So when we compare bond strengths, you need to know this table, okay? And here actually it is filled out for you.
Look at that.
I know, yeah. So if you want to pause and get the real deal here, you can. All right. Yeah. Polar molecules.
File, print. You can print that off.
Yeah, that's true. Yeah, if you're in QuickTime, just file, print. Yeah. Now, we want to talk about dipole and hydrogen bonding. Actually, I use the word dipole here. Sometimes just called dipole.
Dipole.
Yeah, but dipole means that you've got two poles that are attracted to each other.
Kind of sound like diaper.
This sounds like diaper, doesn't it? Yeah. Yeah, you must have little children.
Can you tell what world I live in?
Not mine. Yeah. And then we've got hydrogen bonding. And so let's kind of talk ourselves through this here. Actually, you know what I think I want to do? I want to pause for a second. All right, so let's do a dipole force. Let's say take hydrochloric acid, which is a polar molecule, HCl. And then draw the Lewis structure, it look like this. But of course, we're not interested in this bond right here, which is a covalent bond. We're interested in the bond that would exist between two HCl molecules. All right, now what's going to cause this? Well, these are polar molecules. And if you recall, hydrogen has a electronegativity of 2.1, and chlorine has an electronegativity of 3.0, I think.
I think you're right.
Maybe 3.5. It doesn't matter. The point is that the chlorine is more electronegative than is the hydrogen. Yes. And so if we were to draw this, we would put an arrow through here and put the positive, which means that this side would have a slightly negative charge, and this side would have a slightly positive charge. And that would, of course, be true for the other chloride ion. And that would make this side slightly positive and this side slightly negative. But if you look carefully here, you will notice something. What is that, Mr. Sams?
That the negative and positive are going to attract one another.
You see, what's really causing all these things to occur is that positive things are attracted to negative things. And so this dashed line right here represents the dipole force. Actually, important to note here, it's not called a dipole bond, but a dipole force. Even though it's kind of a bond, since it's kind of really weak, we don't even use the word bond, we use the word force. Yep. And that's why hydrochloric acid sticks together, although it doesn't really do a good job because Heck, I just
HCl is a gas.
HCl is a gas.
Yeah, so.
And in fact, that's an important point. You know, the stronger the bonds, the more solid something is. And if it's a gas, it's held together by weak forces. If it's a solid, it's held together by strong forces, generally speaking. All right. And hydrogen bonding's an interesting thing. It's actually a special case of a dipole force. All right.
It's like a super dipole.
It's like a super dipole. And it is essentially only when you can get F fluorine, O oxygen, or N nitrogen hooked up together with hydrogen, hence the word hydrogen bonding. And actually the word bond is used because we learned just a minute ago it's a strength of 5. Now, there's a good way to remember this. And by the way, F, O, and N are the most electronegative atoms. Yep. They are actually the smallest, and they are small. Remember, the size matters. And they are also the most electronegative atoms. So you get two things together, and then when they get together hydrogen, they make this extremely strong sort of super dipole force. Yeah, it just works like a dipole, but it's 5 times stronger. Now, there's an interesting way to remember how this works. Do you remember that guy?
Yeah, I was 3 when that movie came out.
Yeah, I was like 16 or 18.
Yeah.
Yeah. Well,
I wonder if our kids have ever seen E.T., that movie.
I think mine have, yeah.
I remember watching it in Spanish when I took Spanish in high school. That was kind of fun.
Yeah, well, what did E.T. say?
He said, phone home.
Yeah, phone home. All right, phone. I like it. See, E.T. couldn't spell because he wasn't like from America. So he spelled right? He wasn't from America. Phone home. So E.T. phone home.
Yeah.
So, yeah. And the H stands for home, and F-O-N stands for like phone. Like getting this. He's trying to phone home right here in this picture.
Elliot.
Oh, yeah, Elliot is. You get the idea. All right, if we want to look at it at a different perspective, here's a water molecule. Water has an O connected to an H here, and you can see the positive ends of the hydrogen and the negative ends of the oxygen. And this dashed line right here is the hydrogen bond. And that's what holds water together.
Yeah, hydrogen bonds are pretty strong. Water has strong hydrogen bonds, which is why it's a liquid at room temperature. It's kind of one of those weird things. It's got a really wide range of where it's a liquid.
Yeah.
And that's a good thing because we're mostly water. So, yeah, if that didn't have those strong forces, we'd walk out in the sun and we'd boil away.
Yeah, here's an interesting graph that explains the hydrogen bonding very well. And if you have, for example, H2TE. Now, H2T, if you draw the Lewis dot structure of that, TE, if you look on the periodic table every day, is right below oxygen, the very bottom of it. But and it's a bigger molecule. We'll learn in a minute. The bigger molecules have higher boiling points. And this has this particular boiling point. It looks like a little bit less than 0. H2SC a little bit less. H2S a little bit less. And then
jumps
boom,
up.
June water. What's going up with this? You see, water has the hydrogen bonding. If it didn't, of course, if you were to draw this graph back, water would have a boiling point like negative 90.
That'd be a problem.
That would be a problem because, of course, we would not exist.
We'd all have to live in like Antarctica.
Yeah, well, we all have to live in Mars, I think.
Yeah.
Actually. And that's true. Actually, you'll see this pattern pretty consistently. You also see the same pattern, say, with HF, phone, F and phone home, right? And then there's the N in the phone home, and it's connected to H. And then when you jump down to CH4, guess what it does? See, since carbon is not F, O, or N, it follows the pattern that you would expect.
Yep.
And its melting point is minus like 170 or something, so it's very, very cold.
Interesting.
So this explains the hydrogen bonding pretty significantly. And these are kind of like exceptions to what scientists would expect. And so there's this special case. Because of the high electronegativity of F, O, and N, you make a hydrogen bond. Okay. Now, what about London dispersion forces? Okay, what causes a London dispersion force to occur? Or what causes a nonpolar substance to
stick together?
Now, first of all, a note, they don't stick together, by and large. So a classic example would be oxygen.
Right. It has a very low boiling point.
Yeah, we're in a room filled with oxygen. We're breathing it. You're breathing it wherever you're at, and it is Take a deep breath.
Yeah, we don't have much of it up here.
Yeah, we have a 75% of the oxygen that you do if you're at sea level. But it isn't really sticking it together. But you can stick it together if you get it cold enough, right? All right. So we're talking about nonpolar substances. Now, if you were to draw the Lewis dot structure of oxygen, it would look like this. It's got a double bond. I won't go into how I got that. You can draw it if you want to. But you see, of course, they both have the same electronegativity, so this is a nonpolar molecule.
Yep, and yet we can get it to stick together. I've seen liquid oxygen.
It looks like
it
a clear liquid.
It can be stuck together. Right.
So here's
it's actually blue.
Yeah, actually, you're right. And so here is two oxygen molecules drawn. Okay. And so the question is, what's going to cause this molecule to stick together? Granted, it's only going to happen at a very cold temperature, very cold.
Well, if we remember, most of the space of an atom is electrons.
Yes.
So you've got this very, very tiny nucleus, but the electrons are cruising around the outside. And they're spinning around, they're moving around, they're just kind of at all sorts of places at all sorts of times. And every once in a while, they all kind of end up on one end of the molecule. You expect them to be evenly distributed, and they are most of the time, but every once in a while, they all kind of suck over to one side.
So let's just say, for the sake of argument, for my picture here, if I can draw this, there we go. This electron, for just a moment, scooches over here.
Scooches?
Yeah, because he moves, like you said. And so he scooches. What's going to happen to this side of the molecule?
It's going to get a little bit more negative.
So slightly negative. And this side, of course, over here will be slightly
a little bit positive.
And if we had the same thing occur over here, this electron decides to scooch over here. There's that word. Scooch. He will have slightly...
Actually, it's probably going to go the other way.
Actually, yeah, we're going to make it the other way, yeah. So for a moment, it's going to do the reverse. This side's going to be negative, and this side is going to be positive.
Right, and what it's going to do is that in any neighboring molecules around it, by having a little bit of a negative and a little bit of a positive charge on one molecule, it's going to induce a polarity in another neighboring molecule. It's going to attract an electron to the other side of that molecule.
Yeah, and so even though it's a very slightly positive charge and a slightly negative charge, opposites still attract. Right. Positive things are attracted. Electrostatic attraction we talked about last time, or only a couple times ago. And that's what causes it. And this is definitely, we use the term, and here's actually a picture of the electrons having moved, and the F is my little slightly, because I don't think I had the right symbol when I was making the PowerPoint. This is called a momentary dipole.
Yes.
Write that down. That's an important term. If you're trying to explain London forces on the APChem test, or on the test we'd give you, whatever it might be, you must talk about the fact that there's a dipole for a moment because of the just random motion of electrons. Okay? All right. Now, there is another issue on London dispersion forces and the size. The bigger the molecule,
Sorry, I was looking at the book.
The greater the attractive forces and the higher the boiling point. Now, let me explain that with a picture. Let's say I have two largish molecules. I don't know what these are. 1, 2, 3, 4, 5, 6. These are molecules of hexane. So I have two molecules of hexane.
Hexane is a liquid at room temperature.
Yeah, it is a liquid at room temperature, and actually has a relatively high boiling point. Yeah. The interesting thing is that it is a nonpolar. And one reason you know it's a nonpolar, by the way, if you stuck it in water, it will not mix. Water is polar, and that's something I think we'll talk about later, but I think you know this, most of you, that polar dissolves polar and nonpolar dissolves nonpolar, but they don't dissolve each other. But basically what's going on, because you have these random movement of electrons, you're going to have lots of different momentary dipoles. Right. And what's going to happen is you're going to have, instead of having one possible London force, you will have lots of London forces. And think of it this way, or here's a better picture. Lots of London forces. You ever played with a thread? Easy to break a thread?
Yeah.
Yeah, pretty easy. But what if you took 50 threads and twisted them together?
Yeah.
Easy to break?
Not so much.
Not so much anymore, because it's now almost like a rope or whatever, because you get tiny little strands. Each strand is very, very weak. Each strand, each London dispersion force from our original table has a strength of 0.1, but if you get 10 of them together, you get 1. Yeah. If you get 100, you get 10.
Yeah.
If you get 1,000, you get the idea. For example, I'll bet you know that, say, wax, candle wax, is a solid at room temperature.
It is, and it's nonpolar.
But it's nonpolar. If you dropped it in water, it would not dissolve. But wax is just a very, very large molecule, and that molecule then sticks together, and that's why it's a solid. So you can actually have solids that are London forces, but it has to do with the fact that you have large molecules. Okay? Good? All right. We should briefly talk about just the noble gases.
Yep.
And that we didn't really put them on the table, but noble gases have very, very, very low boiling points.
Can you make liquid noble gases?
Yes, you can. Yeah. Just get it down to.
Can you make solid noble gases?
Yeah. Oh. Well, helium, the interesting one, of course, is his boiling point. No, this is his freezing point. His freezing point is
almost absolute zero.
Yeah, so he's only got about 3 degrees where he's a solid, but you can make him a solid.
Cool.
So that's pretty cool.
How does that work? How do they stick together?
They stick together by London dispersion forces.
Oh, because they're nonpolar.
Because they're really nonpolar.
Yeah, because it's just one atom.
Yeah, it's just one atom trying to stick to another atom.
And they're really small.
Well, actually, the helium is really small, but the xenon is really big compared. Helium is the smallest of all atoms. That's the heliums, the two heliums. And if I've got xenon, since he's got more electrons moving around,
some more London dispersion forces.
More London forces.
So
this way, xenon is minus 111, which is still pretty cold, but is compared to helium, it's downright hot.
Yep.
Yeah. All right. I think we've already talked about that. Okay. Metallic bond. Hey, what's the key player? Is the
electrons.
Yep, it's the valence electrons. By the way, have you realized there's kind of a pattern, ladies and gentlemen, that all bonding is a result of
size.
Electrons. It's electrons. Yeah, it's electrons, and then the size makes a play role.
Yep.
Play role makes it work. Whatever. Defining property of metals is the fact that you have is that metals conduct electrons.
Oh yeah.
And heat, by the way. And you know this. Your mama probably told you this. Do not stick a wire in the electrical socket.
Or a fork.
Or a fork. Why? Why would you not do that?
Well, you can get a little bit of a shock.
It would hurt. Yeah.
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 I did that one time. I was plugging in a lamp, and I had my fingers on the metal part of the prongs. I was like, oh, I wonder what will happen. And I plugged it in, and I got a nice little shock right at my arm.
Yeah. Yeah. Getting shocks is not a fun thing.
No.
No, I've done that plenty of times.
Yeah.
Yeah, that probably explains lots of problems. Okay. So how does a metallic... That's why
you're so awake in the
morning. Yeah. Woo, yeah. Too much playing around with electricity. All right. Here's the deal. I think it's hard to see. This says a sea of roving valence electrons holds metals together. So here, let's take a look at this picture. One thing that's also true about these electrons, since the electrons, these valence electrons, this is a bunch of metal atoms right here, okay, all hooked together. These electrons are free to move, and they just kind of randomly move from one atom to the next. It's kind of like a commune.
Mm-hmm.
What's true at a commune?
A commune, people float around?
No, they don't float around. They share, at least in theory.
Okay.
It's like the utopia and all that stuff.
I get it.
It's not your stuff or my stuff, it's our stuff.
Okay.
You see.
I get it.
So it's all my stuff. I mean, it's not my stuff, it's all our stuff, right? And so these electrons, this electron does not belong to this atom. It belongs to all of the atoms. And so the electrons kind of randomly move around, and if you get an area that has more electrons for just a moment.
It's kind of like the community bikes you can just like pick up in Portland and go for a ride.
Yeah. Or Paris. I heard it's in Paris.
You just grab a bike and you ride, and you leave it at the community bike spot, and you need another one, you grab a bike and you go for a ride again.
Yeah, and so if you get a bunch of bikes over on one side of the city, and let's say a bike is an electron, which has a negative charge, then that side of the city has a negative charge.
Yeah.
And when the bikes move to the other side of the city, probably because they commute back home or whatever, then you see more
negativeness
on that side, but then it makes the other side positive. So you have like regions. So you'll have positive regions and negative regions. And guess what? Positive things are still attracted to negative things.
Yes, they are.
It doesn't change, does it?
Yeah. And since the electrons are free to move, that explains why it conducts electricity.
Yes. So that's what's holding. So if you're wearing a ring, so everybody who's watching this, if you get some kind of metal object around you, I want you to pick it up. All right, pick it up. So I have a metal object right here on my finger right here. This is my gold ring, my wedding ring. And this is being held together. I want you to envision, get your brain around it, that this particular ring, there's electrons moving around, creating small little regions of positive and negative charge, which causes the gold to stick together. What are you doing?
Trying to get my brain around it.
Oh, yeah.
It's not working so well.
Yeah, I wondered. Yeah, you definitely need some help at this time in the morning.
A little more coffee ought to do it.
There we go. All right. So, and just an interesting thing about metals that I think it's interesting to talk about is there are something's called alloys.
Mixtures of metals.
And in the mixtures of metals, there's two varieties of alloys. There are substitutional alloys and there are interstitial alloys.
Hey, this looks like it might have to do with size.
Yeah, it does. And actually, I almost need like a blank screen. I want to do something here. Oh, I want to hold on. I didn't do that right. So if I were to look at a metal atom, or a metal set of molecules, what you would find is there would be holes in the molecule, or it's not really a molecule, in the
there's a hole
in the bucket, the metal, yeah. And the problem is that it would look kind of like this if you were to take a look. And in fact, actually, interesting thing, why are metals malleable, meaning bendable?
Because there's holes?
Because there's holes. Because as you bend a metal, take a metal, And of course, you can bend a metal, right? Take like an aluminum pop can, right, and you can bend it, right? What happens is that because there are holes, is these molecules, as you bend it in one direction, they slide into the holes, creating other holes, however. And so that's what's going on. But if you want to make a more rigid metal, you fill the holes.
Cool.
And those are called alloys. And there are two varieties of holes. And so if you look at this picture of copper and zinc put together, make the alloy brass. And so copper is the main one, but you see the holes are where these purples would have been.
Does that mean the more holes it is, the more malleable it is?
Yes, it does.
So like lead would have lots of holes?
Because it's very malleable. That is exactly correct.
You know, I learned something today. I'm not sure I actually knew that.
Yeah.
That's kind of cool.
So the substitutional alloy, basically you fill the holes with zinc in this case, and you make the alloy called brass. And another important one is steel.
Carbonized steel.
And what they do is it fills the tiny holes that exist. See, there's like a little tiny hole.
Yeah, in between.
And there's a car, the interstitial alloy.
I like that
and
word.
I love that word. And it's called steel. And they fill the tiny holes. And actually, they don't actually even use another metal. They use carbon. And it's pretty fascinating because it's tiny. I actually had an interesting experience. I got to see them making steel one day. I was down in Pueblo it was a class I was taking, and they have a steel making factory in Pueblo, Colorado. Those of you who are outside of Colorado, and we were standing 200 feet from this vat, and this vat, was a huge vat filled with molten steel. They had electrolyzed it, put electricity in it to melt it. That's how they got it, and it had this big old lid. And this big thing is now probably 2 stories tall, and it's got a diameter of 30 feet. It was absolutely huge, and we're like 100 feet away, and it is the hottest place you can imagine, just standing 100 feet away at this balcony watching this occur. And this dude, okay, there's this building, all right, there's this building right next to this, or we're in a building, but there's a building in the building, if you will, or a little room. He comes out of the room, and he's wearing super heavy clothes and totally like in the winter.
Reflective hot suit thing?
Yeah, it's like a hot suit thing. And he just takes somebody else in the room. He takes and he opens this thing, the lid electronically, I assume. And this guy takes this big old 50-pound bag. He throws it in there, and it catches on fire. And then it just descends in there. And what that was, our tour guide told us, basically this was the carbon. And actually they also use some molybdenum. And they add the carbon and the molybdenum to make the steel just the right strength. And there's somehow some kind of an auger down here that stirs it all up, mixes everything together. And then this thing, it was on...
what's that auger made out of?
It's a good ceramic, I would have to guess. And it's on this conveyor belt. It's going on this conveyor belt. And eventually the thing tips over, and then the metal pours out. They were making railroad rails, and it went into this form, and then eventually, and the form was made of ceramic, which has even a higher. Ceramic is held together by network solids, so therefore it didn't melt the ceramic. And cool. Eventually they cooled it, and we went to the cooling room, which was still very hot, and then eventually they took the rails and put them on the railroads. They actually put them on trains. And then took them to wherever they needed to put them.
I saw them making bathtubs on TV one time, and they had sand molds. They made molds out of sand, and then they poured the metal on top of that. That was kind of cool.
Yeah. Speaking of sand and ceramic.
Oh, yeah.
We're going to talk about network solids. Hey, and a network solid, it's a molecule that has all covalent bonds. Now, interesting thing about this, of course, we've talked about this. Covalent bonds are the strongest of all bonds. They have a strength of 100.
Yes.
So these only applies to 2 varieties of elements. Yes. 2 elements. This only applies to carbon and silicon.
Oh, silicon. Sorry, not silicon.
You're still awake. Still asleep.
It's an S element.
All right. The examples of this are diamonds. I'd love to show you diamonds, but I don't have one. My wife has a diamond. Diamonds.
They are a girl's best friend.
Graphite. Quartz. These are the big 3 to remember for these things. And sand, Mr. Sams was just talking about. Sand, of course, is quartz, silicon dioxide, and has a very, very high boiling point and melting point, too, for that matter. All right, so diamonds here. And this is graphite. Graphite, by the way, is in a pencil.
Yep.
So,
now,
go ahead.
Real quick. Diamonds, very, very hard.
Yes.
Okay, and those are held together by these tetrahedrally arranged carbon atoms. And so that's very strong. A force value of 100, like we were talking about. Now the graphite, notice they're held together in these sheets. The sheets are kind of cool. you've got these little hexagons that are stuck together. And you know graphite, it's kind of slippery. That's why your pencil moves across your paper. It's because those sheets kind of stack on top of each other. They don't attract to each other really well, so they slide across each other, which is what makes graphite slippery.
And the weak bonding of the layers is held together by London dispersion forces. That's why when you write with a pencil, it's going to come off on the paper, but it's very, very strong, sticking in the flat plane.
Like locks in your doors, they use graphite as a lubricant. They just shoot it in there, and it makes it all slippery.
Yep, it's very, very cool.
Yeah. There's actually one other allotrope of carbon, too, that we don't really talk about a whole lot, and that's called a buckyball.
Yeah.
And it basically looks like a soccer ball.
Yeah.
They're actually doing a lot of research with it now, like putting things in the buckyball and using it to deliver things in really small quantities.
Yeah. So here, folks, interesting picture. This is actually Mr. Sams was talking about a buckyball, and this is the structure of the buckyball. These are all carbons held together in a they're sp2, aren't they?
I don't know.
They're all held together by three.
They're
There's
not really
three.
planar though, so I'm not sure.
Yeah. Anyways, but that's what buckyball looks like.
Yeah. These are also called fullerenes. The person that came up with these, Buckminster Fuller. So Bucky from Buckminster, or fullerenes from his last name.
Yeah. So that's kind of cool, I think. Yeah. So that's the buckyball. So I think it's intriguing to kind of look at that. All right. And graphite again.
There's your graphite layers.
And then actually, let's take a look real quickly. This is the silicon oxides are the ones that primarily. There's a number of varieties that they call silicates. Some of these are silicates.
Yeah.
And then
tetrahedral.
Yeah. And then you've got S's and O's, basically. And the S, I believe, is the yellow. Yeah. And then the red is the oxygen in this picture. So,
So
if you see SIs and O's, you've got a network.